Hello class. Today we are going to begin by going over any homework questions that you have. Please put these on the board and spend a little time having you guys answer each other's questions. Ms. Zeidler, if you wouldn't mind noting who volunteered to answer questions for the rest of the group, please pause the recording at this time to go over homework questions. Okie dokie. Today we're going to talk about matrix inverses. In the beginning of this chapter, I stated that there were going to be many ways we were going to learn how to solve equations, specifically how to solve systems of equations. So today we're going to learn a brand new way to solve systems of equations, and it involves using matrix inverses. So before we jump into how to find and use matrix inverses, we're going to look into some properties of numbers so we can understand what those properties are, what the specific names of the aspects of the properties are, and then we're going to apply them to matrices. So first we're going to look into numeric definitions. So we have the numeric definition of an identity, and we have two different identities. So numerically, an identity is what you operate with to keep the number the same. So the question you need to ask yourself is, what do you add to a number to keep that number the same? And the answer is 0. You add 0 to a number to keep it the same. And the multiplicative identity is what you multiply a number by to keep the number the same. So I think of identity as like what you are, what keeps you you. So what keeps you you, or what is your identity, or what a number keeps a number itself is its identity. So a multiplicative identity is going to be, I don't know why I wrote that line here, let's erase that. A multiplicative identity is the number 1, because multiplying by 1 keeps a number the same. Then we have an inverse. Now inverse is what we're going to be using a little later to solve matrix equations, but we need to know what a numeric inverse is. So an inverse is what you operate with to produce the identity. So what do I add to a number to get the identity? So I add something to a number to get the identity. So the additive inverse is going to be the opposite. So it's the negative or the opposite. So if I add the opposite, I get 0, or the identity. So that is the additive inverse. If I multiply by the multiplicative inverse, I get the multiplicative identity. So in other words, what do I multiply a number by to get 1? And the answer is going to be the multiplicative inverse, or the reciprocal. So we have these two concepts. Identity is what you operate with to keep the number the same, and then inverse is what you operate with to produce the identity. And we have these same concepts with matrices. Also, we need to talk about matrix multiplication. Matrix multiplication is not commutative. We learned about that the very first day we talked about matrices. You can't multiply two matrices in any order and expect to get the same result. A lot of times you can't even multiply two matrices in one order and then even be able to multiply it in the other order. So for example, a 3 by 2 matrix, if you multiply it by a 2 by 5 matrix, you can do that. You'd get a 3 by 5 matrix, but you cannot multiply it in the other order. So you cannot multiply a 2 by 5 matrix by a 3 by 2 matrix. That does not work because these are not equal. So matrix multiplication is not commutative in general. What matrix multiplication is it is associative. Associative allows you to change not the order in which you multiply, but it changes the grouping. So if you have three matrices being multiplied, matrix A times B times C, you can either multiply B times C first, get that answer, and then multiply that result times A, or you can multiply A times B first, get that answer, and multiply it by C. It's really impossible, or virtually impossible, to multiply all three together all at once. So you multiply two of them together, get that answer, and then multiply it by the third in either way, and you'll get the same result. Also, with matrices, you do have a distributive property. You can add two matrices together, get that answer, and then multiply it by A, or you can multiply A times B, multiply A times C, and then add them together. I probably would do the operation on the left side because it requires less multiplication. It's just faster. Now, what we have here are two square matrices which make up what are called the matrix identities. Now, remember before we talked about multiplicative identities. The multiplicative identity for numbers is 1, because if I multiply a number by 1, that number doesn't change. So the matrix identity works the same. If I multiply by a matrix identity, the matrix doesn't change. But because matrix multiplication is only possible if the dimensions are correct, I have to have different identities depending on the matrix that I have. So I have I2. I2 is the matrix identity that's a 2 by 2 matrix. I3 is a 3 by 3 identity matrix. And you can imagine what I4 and I5 would look like. I1 is just a matrix that has a 1 in it. So the qualities of these identity matrices is they have 1s along the main diagonal and then 0s everywhere else. So on your I2 you have 1, 0, 0, 1, I3, 1, 0, 0, 0, 1, 0, 0, 0, 1. And so what we can do here is show that these are truly the identity. I don't know if we'll have to do all three of these, but we certainly can if we want to. So the first thing we're going to do is find A times I3. I'm just going to scroll up a little so we can see I3. So A is given up here. And because A is 2 by 3, we would need to multiply by I3 because the leading dimension, or the number of rows in the next matrix, would have to be 3, or else those middle dimensions would not agree. So if I multiply by I3, which is our 3 by 3 identity, if it is in fact a 3 by 3 identity, I should preserve the original matrix. So remember, to multiply, I do row by column. So 3 times 1 is 3. Negative 2 times 0, 1 times 0. That's zeros. Then I do row by column. So I have 3 times 0 is 0. Negative 2 times 1 is negative 2. And then 1 times 0 is 0. So far so good. Now I'm going to do row by column one more time. Row by column. So 3 times 0, negative 2 times 0, 1 times 1. Hey, you guys see that? I have preserved the first row of A. So far it is acting as it should. So now I'm going to do row 2 times column 1. So I have 0 times 1 is 0. 4 times 0, negative 1 times 0. Beautiful. Now I do row 2 times column 2. 0 times 0, 4 times 1. Oopsies. Whoopsies. 4. And then, let's see, negative 1 times 0 is 0. And then lastly, we'll do 0. That last row times the last column, 0 times 0. 4 times 0, negative 1 times 1 is negative 1. And we can see then that this equals A. Yay, that equals A. So you can see that multiplying by the identity matrix, which is given right here, I3, I have preserved my original matrix, matrix A. And that's what an identity does. When you multiply by an identity, or you add by an additive identity, the numeric quantity, or in this case, the matrix quantity, does not change. And the beautiful part about identities is they are commutative. So it is one thing in matrix multiplication that you can do commutatively. So if I were to multiply I2 times A, it actually would work. And I would do it, but this is going to take a long time. So if I did I2 times A, I would get A as well. So multiplication with an identity is commutative. And it's really the rare case where you can multiply by I in the back or I in the front, and it both works. You still get A. So that is what an identity matrix does. It keeps the matrix the same. So here is the identity property demonstrating just that if I multiply by the identity, the matrix stays the same. And you can left multiply or right multiply. It all stays the same. So that works. Okay, now we have what is called a matrix inverse. So we know that an additive inverse is an opposite. So if I add a number and its opposite, I get 0, which is the identity. If I multiply a number by its multiplicative inverse, like 4 times 1 over 4, I get the identity, 1. So if I multiply a matrix times its inverse, what do you think I'm going to get? Let's see. Okay, so I'm going to do row by column. So I do row 1 times column 1. So I do 3 minus 2, row 1 times column 2. So I have 3 halves and a negative 3 halves. And then row 2, column 1, negative 4 here to here, and then plus 4. And then row 2, column 2, negative 2, for 4 times negative 1/2, and then plus 3. So I get 1, 0, 0, 1. I get the identity. So if you multiply a matrix by its inverse, you get the identity. Just like when you multiply a number by its multiplicative inverse, you get the identity. Same thing, but the question is, how do you find this inverse? Is that a magical operation? How does that happen? The inverses are so important because they allow us to solve equations. If I have the equation 4x equals 16, no, let's do 20, the way I solve is I multiply by its inverse. Okay, so that's why inverses are so cool. They allow us to solve equations. So we need to know, how do we come up with a matrix inverse? So if we look at this system, we can write it using matrices this way. So what we do is we take the coefficients of x and y, write them as a 2 by 2 matrix. So it's 3, -2, 2, and 1, just picking them off. As long as the equations are lined up properly, that equals 4, -3. So this is how we represent our system. And do notice if I multiply these together, let's see, if I do row by column, I get 3x minus 2y, and then I do row by column, and I'd get 2x plus y, and that would equal 4, -3. So you actually get the same thing if you multiply it out, so I just wanted to show you that that is indeed the same. But anyway, you can take this system and write it as a matrix like that, and then we can solve it. So the way we solve it is we call this matrix A. We call this matrix X because it's our variable matrix, and we call this matrix B. So if I gave you the equation AX equals B, and you guys were asked to solve it, you would say, oh, I'll just divide both sides by A, and I'll get X equals B over A. Well, that's okay with normal numbers, but as I said the first day we talked about matrices, you can't divide by a matrix. So let's get rid of that. So instead of dividing, I'm going to multiply both sides by the inverse. So if I multiply both sides by the inverse of A, and I have to multiply on the left for both of them, because matrix multiplication is not commutative. You can't multiply one side on the left and one side on the right. That is not okay, because left multiplication and right multiplication is not the same thing. So now, A times A inverse, we know if we multiply a matrix times its inverse, we get the identity. And then we know the identity times any matrix is the matrix itself. So the way you solve this is the solution X is A inverse times matrix B. So all we need to do is figure out how to find A inverse because we know how to matrix multiply. You have that skill intact. So this is how you solve a system using matrix inverses. Wow, that got way worse. Let me undo that. Okay, we'll just leave it like that. Maybe. There we go. Yay. All right. So the way you find an inverse is the following. If you have matrix A, which is given by the elements A, B, C, D, listed left to right, up to down, A, B, C, D, the inverse is defined as 1 over the determinant. Okay, we learned how to find determinants in the past 2 sections, times dA. So notice these 2 elements were switched, times, and then the opposite of B, the opposite of C. So the main diagonal was switched, the opposite diagonal was negatized. And that is the equation for the inverse. This seems confusing. After a while, it's going to be as easy as adding and subtracting. It will become very second nature. And if you get to linear algebra, after you take calculus, you'll learn why this is true. But at this point, it's just one of those formulas like the quadratic formula that you just learn. So A inverse is 1 over the determinant of A these are switched, these are negatized. Now, if you end up with a determinant of 0, what happens is the determinant is singular. So singular means there is no unique solution to your matrix. And if there is no unique solution to your matrix, that means there's either an infinite number of solutions or no solution. So in this one, the determinant is 24 going along the main diagonal minus 24. So that means, therefore, there is no unique solution. Because when you look at the equation for the A inverse starts as 1 over the determinant. So 1 over 0, you can't solve it because you can't find the inverse. So if there's no unique solution, then you cannot solve the equation and find a unique solution using matrix inverses. So singular matrix. So let's get back to our problem. The way you solve these, first you find the inverse of the square matrix. So I'm going to label A, B, sorry, that's not B, undo, A, X, B. X is always given the variable matrix. Find the inverse of the square matrix. So A inverse is 1 over the determinant. 1 over. So let's find the determinant. The determinant is going to be 3 minus negative 4. So 1/7. So A inverse is 1 over 7, 1 over the determinant, times, we're going to flip the main diagonal. So these get flipped, these get opposited, they get negatized. So the 2 becomes a negative 2, this 2 becomes positive, this 2 becomes negative. So this is A inverse. So again, you flip along the main diagonal, you negatize this diagonal. 1 and 3 are switched, this 2 becomes positive 2, this 2 becomes negative 2. And then our equation is X equals A inverse B that we derived on the prior slide. So A inverse is 1/7 times 1, 2, negative 2, 3 times B, which is 4, negative 3. So now I have to actually multiply. So what I'm going to suggest is that you multiply these together first and then multiply in the 1/7. So row by column. 1 times 4, 2 times negative 3, and then here to here, row by column, negative 6, whoa, negative 8. Wow, that was not good. Let me get rid of that one. Negative 2 times 4 is negative 8, and then that's going to be negative 9. Let's close my matrix there. So X equals 1/7 times negative 2, negative 17. So my matrix X is going to be negative 2/7, negative 17/7. So X comma Y is negative 2/7, negative 17/7. Woohoo! All right. So recapping, find the inverse. 1 over the determinant. We flip the diagonal, negatize the other diagonal. It's the inverse times B. And to multiply, we multiply the two matrices together, and then we distribute it in 1 over the determinant. And that's our answer. Pretty cool. And you can plug it in to check, make sure it works. Okay, let's do another one. So I'm going to set up my matrix. That's AX equals B. I'm going to find A inverse. So it's 1 over the determinant. Now the determinant is negative 1, -1 minus -6, so it's +6, so it's 5, so it's 1/5. And then I'm going to switch the main diagonal, negatize the other diagonal. So that's A inverse. So then x equals A inverse B. X equals, sorry about that, A inverse B So again, I'm going to multiply the matrices together first, row by column. So I get -11 plus 16 is 5. And then I get -33 plus 8 is -25. So that is going to be 1, -5 when I distribute in 1 over the determinant. So xy equals 1, -5. So then my answer is 1, -5. And then if I check, 1, -5 works up here, 1, -5 works up here. So again, A inverse, 1 over the determinant, switch along the main diagonal, negatize here. That's my inverse, and it's the inverse times B. Multiply the two matrices together, and then you can multiply in 1 over the determinant. And it will work every time that the matrix does not have a determinant of 0, meaning it has a unique solution. There is your homework. Hope you guys have a great 3-day weekend. See you Monday.